Next one, 3.44. Again about determinants, but also very importantly now about inverse matrices. Better speaking, one inverse matrix, how to construct it, how to calculate it, its values. Okay, so there are different methods to do this, but this is the standard method we're using here. The first thing is we look at this system of linear equations, which is inhomogeneous again, as we see. So we have some numbers here which are unequal to 0. Then firstly, this is boring. Now, meanwhile, it's boring to calculate the determinant, but anyway, I have a click run doing this, and then, okay, answer is a invertible. What does this mean? And so on. And then do these steps to find the inverse matrix and use it afterwards to solve the inhomogeneous system of linear equations, which is, again, an interesting connection between matrices as such and the corresponding systems of linear equations. You may know, I don't think Martin told you, but you may know anyway, that you can also find the inverse matrix by using an extended, yes, I think he even told you, using an extended notation of the Gauss-Jordan elimination. Performing the Gauss-Jordan elimination using an extended notation with a unit matrix on the right side, you know what I mean? And then this unit matrix step by step transforms into the inverse matrix, a to the -1. That's a nice method, I must say. Okay, but we're not using it here. So let's see. What's the best idea to find the determinant? I would say it's developing along the third column. Why? Because this is the, well, I could also use this second row perhaps, but anyway, this is a column where there's a 0 inside, so I have one contribution less. Okay, that's a good idea. And then you remember how to do it. I refer again to this sign scheme which we had, plus, minus, plus, always changing. So this time, obviously, we have to use, again, plus, minus, plus, much the same as before with the first row. Okay, so we do it, -2, take it as a factor, crossing out, remaining submatrix called minor is -3, 1, 1, -4, and so on. The second, the second I don't even have to write down because it's a factor of 0. And then I have a plus sign again, 2 times. Where is it? Here, plus 2 times, and then crossing out, 4, 2, -3, 1. So that's quite easy. What do we get here? Take care, the product is 12. -3 times -4 is 12. -1, so then it's 11. But -2 times, -2 here times 12 -1. The next contribution is +2 times, and then 4 -6. So in parentheses, I have 4 + 6. What is it? -22, 2 times 11, plus 20. So actually, the result is -2. Here, I wrote it down, okay? A few steps. It's not equal to 0, and that's all. And that means it follows its invertible. We know this, okay? It's not singular, it's invertible. And this, again, means that the inverse matrix A to the symbolic notation A to the -1, okay, exists. And the fact that it exists also means, of course, that this system of linear equations has a unique solution. But how to use the inverse matrix in order to find the unique solution is another interesting aspect. So second, what about this adjugate matrix A adjugate? This is something special, and it requires a few steps to get to what we want and what we need. Okay, I just do it, and supposing you know what I'm doing. I construct, I call it C. This is, I don't know if this is standard notation, but I construct a C matrix. Its elements are just, well, C11, C12, and so on. And then I will use this C matrix as a fundamental, or as a basis for getting my educate matrix. So this is a few steps before. You know that this is similar to the Laplacian expansion method for determinant, but it's not the same. So C11. There's also a sign scheme which is much the same as before, this chessboard sign scheme, but I put it here explicitly. If you don't want to remember any chessboards, you just take a -1 in parentheses, and then you take this to the power of row number plus column number. And since 1 plus 1 is an even number, you get a positive sign. If you have of course, you have 1 plus 2. If you have an odd exponent, you get a negative sign. That's all. Okay. So I use this scheme here, but without, that's important. I do this crossing method, but without using the factor. You know what I mean. This time I must not mix it up with the determinant method. I actually, if I say C11, I do delete first row and first column and use the remaining minor. But this time I do not use the factor for anything. Okay, that's important. Now, so like I said, 1, 0, minus 4, 2. What is the determinant here? It's 2 minus nothing. Okay, just 2, and this is the positive sign. Next one, C1, 2. Here, 1, 2, always looking at matrix A and doing my deletion, performing my deletion operation and constructing my minors. By the way, some of them we already used before. Where is it here? But these are different ones. Yeah, they come later. Okay, 1, 2, minus 3, 0, 1, 2. So what remains? You can follow me. So this time I have a minus sign. Here the product is minus 6, minus 0 again, but minus 6 is positive 6. C1, 3, first row, third column, crossing out, minus 3, 1, 1, minus 4 remains. Here the determinant is product 12 minus 1. That's one we had used before. You remember? 12 minus 1 is 11. And this is a positive sign again. Right. So that was for, that's it for the first row of this C matrix. By the way, the first, you may know that the adjugate matrix, which we want to calculate, to construct, is also the transposed version of the C matrix, more or less, okay? And so although this is the first row of the C matrix, these numbers which are now written here as a column, sort of column, are in the end, they are the first column of the adjugate matrix. Is it 2, 2, 6, 11? If we look here. Right, this is the first column. Okay, so it's just the performing the transposition of a matrix C to get the adjugate matrix. Now, let's go on here. C1, C21, I go to the second row, cross it out, and the first column. Remaining numbers are 2, minus 1, minus 4, 2 here. Then 4 minus, but here the product is 8, as you see. So 4 actually plus, am I right? No, I must be careful. Wait, 2, and here the product is 8, right? But I must subtract it. So 4, and that's really, I don't know, almost I would have said 4 plus 8 is 12, but 4 minus 8 actually is negative 4, and it's a minus sign. I don't put this notation anymore. Okay, you see 2 plus 1 is odd, so it's a minus. And then I get minus 4 is 4. That's it, positive number. So the next one, oh, please, I don't want to bore you. I will stop in a while with this detailed presentation. 2, 2, 4 minus 2, 1, 2 are the remaining numbers. This is the minor. Product is 8. Other product is negative 2. 8 minus negative 2 is 8 plus 2 is 10. Positive sign, 2 plus 2 is even, okay? Now, one more step. 2, 3. Second row, third column, crossing out. What remains is 4, 2, 1, minus 4. 4, 2, 1, minus 4. Product is minus 16. Product is 2. Minus 16 minus 2 results to negative 18. A minus sign, where does this come from? That's 2 plus 3 is odd. Okay, right. So minus negative 18 is positive 18. And then I really shortened the rest of it. Now you mean why you really know how to do it. And the results for the third row of the C matrix are 2, 6, 10. So that's all. And these are, in the end, the columns of the educate matrix. Just try to remember these numbers as columns now. 2, 6, 11, 4, 10, 18, 2, 6, 10. Look here. 2, 6, 11, 4, 10, 18, 2, 6, 11. So I just transposed the C matrix to get my educate matrix. And this is almost the inverse of A. The missing step, of course, is to consider the determinant. And you may know, I mean, it's not really a miracle. It's the fact that the product of a matrix and its inverse matrix must, of course, always be the identity matrix. But the identity matrix has determinant 0. Now that's quite interesting to show this way. If I use the theorem of, determinant, I don't know how it's called, but the theorem of before, where we said that the determinant of a product is the product of the determinants, okay? So I can say it must be the case that this times this is this. And here, the determinant of the unity matrix, of course, is 1. And now this is that A. And it means that this must be the reciprocal of that A, because otherwise I wouldn't get 1 here. So that's quite obvious, okay? And this is what I'm doing. I will divide each and every element of this educate matrix now by the determinant of A, which we had calculated much, some time ago. I have forgotten, was it -2? Yeah, it was -2, right? So just do it, divide by -2. 2 by -2 is -1. So I get, these are all positive, these are all negative. And then half the numbers. 1, 3, 11 half, this is a fraction, of course. 2, 5, 8, 2, 5, 9, sorry, but all negative. And then 1, 3, oh, where am I? 1, something's wrong. Is this a notation mistake? What I'm doing here. Yeah, 2, 6, 10. Why? Didn't I read it and check it? Okay, I don't know. It's a mistake, right? Do you agree? Must be 10, right? Yeah, otherwise I don't get. Dividing by -2, I get -1, -3, -5. Now it's okay. So since this is definitely the inverse matrix of matrix A, now this is to the third one, finally. This is the nice point. We can put any system of linear equations into this matrix vector form. So this is a short notation for the whole system of linear equations, which says the coefficient matrix A times the vector of unknowns, vector x, equals the B vector, which just contains the right-hand numbers of all the equations. So since this is a valid matrix vector equation, just imagine I would multiply the inverse matrix of A, which we just found, from the left side here, then it would neutralize matrix A. A inverse times A results, we just had it here, to identity matrix. So this isolates my vector of unknowns, x. But then I must also, from the left side, I must also multiply the inverse of A onto vector B. And that's all we have to do. We apply this matrix to the B vector, and then it transforms, you can say it transforms to the solution of the SLE. If it's a great method, but it's the bad message is it's so much effort to calculate the inverse matrix. What a pity. Okay, but that's it. Remember, the numbers are -2, 6, -9. And then the usual procedure, Erteg principle. First row, type it, I forgot again, -2, 6, 9. Let's just make a little test. I put it here again. -2, 6, 9. So first row times first column would be 2 -12. This is -10. No, what am I doing? 2 -12 is -10, and then -9. You know, this is it. You don't help me. Why don't you help me? This is a minus here, isn't it? Look, the b vector. -2, 6, -9. This time. -1 times -2 is 2. 2 -12 is -10. And then +9. -10 + 9 is -1. So, and the same thing for second row column, third row times column, we get -1, 3, 2. These are the solutions for the 3 unknowns. Okay, so this is x1, x2, x3, and we can test them. We can test these values. I would recommend to do it if you have the time, just for well, for your own control. Just test it, and if you put these into the original SLE, you will find that all the equations are fulfilled. So that's all I have to say about determinants and inverse matrices. I hope you enjoyed it, and I hope to see you next time. Well, also, if you have some questions, of course. I see. We even have some time left. Bye-bye.